going to talk about deforming oscillators. So like Miller has demonstrated that oscillators can never die. And we got to honor that tradition. And so this is another anti-death motion for oscillators in just a slightly different perspective. So I like cartoons, and this is the one-slide summary of this talk. I think it's fair to say that when we think of oscillation, that we think of sinusoidal oscillations. In fact, in many programming languages for music production, OSC for oscillator literally means the sine oscillator. And so it's the canonical thing of oscillation that we're trained to think about. And I have 43 minutes. I like it. So the goal of this talk is to tell you that like we have this whole zoo of techniques that all are oscillatory-based, FM, and so forth. But we don't have to do them on the circle. We can do them on very general topological spaces as long as they're loops, and we can make them look crazy like the thing over here or even crazier. And so I'm going to sort of walk you through how we get there. And quite a bit of this is a review of earlier work. And the first step is that rather than think of sinusoidal functions or complex phasors, we're going to think about points on our circle where we iterate positions, right? We have point xn here, and we have some function that gets us to some future point xn plus 1. This is a perspective that's actually very popular in the dynamical systems literature. This is a discrete dynamical system on the circle. And if we write how we would now synthesize, of course, we want audio samples in the time series. This is just our standard output. But as our dynamics we have this discrete iteration with this function that gets us from a previous point to the current point. And this mod 1 forces us on, if you want, the circumference on the circle. That this thing numerically gives us a circle topology. And then, we're just on a circle. Then we might want to decide how we project that out. And the conventional thing to project a sinusoidal oscillator out is with a sine projection. But orthogonal projection is going to get us what we are happy and familiar with, right? The big point I want to emphasize here, and you guys are sick of me talking about topology, but the big point here, you should think of this, we're going from a point on a topological circle to another point on a topological circle. And in a way, like I don't actually reference any circle function in this particular equation, but we no longer really think in terms of a hard embedded circle in a Euclidean plane. This is just sort of an abstraction of a circle. Well, all we require is that we have some parametrization around the circumference of this abstract circle. And even just in this picture, you can sort of unify a lot of the synthesis methods that have sprung up over the years. They can just be rewritten as iterative phase functions, and we get a more clear picture which ones were explicit about what projections they wanted to use and which ones weren't, and we find a bunch of them are chaotic, and so forth. And the bottom thing actually, in a way, summarizes all of these. You can find some way to actually morphologize or interpolate or incorporate all these techniques as sort of a one big technique if you want to go crazy. And so the program that we're going to engage in is demonstrate the process on these four examples in this diagram. The sine oscillator, just because I have to. I just praise this to high heavens. This is our holy grail. Frequency modulation, because it's the second holy grail. And feedback FM, because it's actually the thing that nobody uses. And the sine circle map, because I ended up writing a paper a long time ago about this, and only in 2019 realized it's the same thing as feedback FM. So this is an embarrassment for me, but it's good to know. But you see there's actually a difference, right? In the dynamical systems, the sine circle map does not define a projection, and feedback FM does define a projection. So that's a difference, but it's a very, very pedantic difference. So for all practical purposes, we're going to think of them as being actually identical. And so what we're going to do is, right, so this here I've just written down feedback FM, right? So the way you can read this is, so this is our iteration on the circle, previous position, future position, but there's also previous position here. And omega is just a constant. So this part is just a sinusoidal oscillator. We step around the circle in constant steps. And this part here is our modulation, but you can also think of it as a perturbation that's defined by this strength coefficient here. If this is 0, it vanishes. If it is very big, this term is going to dominate. And it's a sign because FM is a sinusoidal modulation, and it's feedback because we're going to get our frequency not from an independent oscillator, but from a previous value. So this is literally just an unfamiliar way of writing feedback FM, and mod 1 just makes sure it stays on the circle. Like this enforces the circle topology. And we can project it out with a sine function, and this is then literally what the patent is on feedback FM. And what we're going to do is we're going to say, like, sorry, sine function, we want you to be more general, right? So instead of having these sine functions, we now have general projection functions here that we make our playground. And in fact, we're going to make it a little bit more than just projection functions, our playground. But this is sort of the equational generalization that we're doing here. And just a quick interlude about embeddings and stuff. You guys heard about this earlier, and I don't want to torture you too much. But for a topologist, everything that's here in this area, that is actually a circle. So this puzzle piece is a circle. This is the circle. Heart's definitely a circle. It's because they're connected like circles. And for this paper, we require that we can find some parametrization around this curve. Right? In some of these cases, I trust that you can do it. For these piecewise linear things, you could just write out piecewise linear function, you could do this. Maybe you have some nice function for this. In any case, or you do some spline interpolation. Let me actually skip this part for now, and we might actually come back later if there's time for that. So the way we're thinking about this, often it's actually convenient just for us to have some reference, to not think of abstract phases on some abstract circle that doesn't have any other existence, but give us some sort of visual representation that we can play with. So we're going to take this topological circle, and we allow ourselves to actually lift it up in some higher dimensional space. So this can be a curve in a higher dimensional space. And by high dimension, I mean 2+. So a plane is higher dimensional. And from that higher dimensional space, we can then project down, find some nice projection function onto an audio sample, right? And this recipe already gives us a generic way to actually define any projection function. We just define a projection function from the abstract circle as the composition of our embedding with this down projection, and that's what this equation says. Now, a neat thing about thinking about these representations is that audio is just a segment of a line. It's a low-dimensional space, but we have this oscillatory phenomena, as in Miller's example, in these higher dimensional spaces. So we have a lot of freedom to exploit these for control or for visualization or whatever else you want to do with that. And I sort of try to capture this notion here. Let's say you have a high dimensional thing here. You want to do a planar representation that you can put on a screen. You can have another projection that comes out of that oscillator, just gives you some nice visualization. And they are related in some sense coming from here. But this one is not meant to be invertible. So it's not, I don't guarantee we come back. And that's sort of the explanation for these figures. We can even have visualizations that look kind of gnarly. And that's fine, because ultimately our dynamics is coming here, and we're just going to guarantee this projection. And all of this you can think of helping us control or visualize. Okay, so this is all abstract, and I wanted to give you something concrete. Right? So what I said is all you need is a parametrizable function that closes onto itself. Whatever that is, that will work in this construction. And I wanted to give you one concrete one. And so what I'm going to take is the Catmull-Rom spline with a tension parameter. Right? This is a simple spline, and I picked it because it's very easy to use. Right? So the way the Catmull-Rom spline works, I want to interpolate between these 2 points, and I provide 2 additional points, a point before and a point after. And these 4 points will give me all information I need to then be able to interpolate parametrically over this line segment here. But this continues. So if I shift over one and want to interpolate here, I can keep this control point and just add a new one down here. So it's a nice sort of iterative process that you get in your interpolation, where a control point is also a point that you're going to use as an edge point in your interpolation. So it's just a very nice setup. So I have 52 minutes left. Perfect. Okay, so this is just a polynomial and no one cares. The only thing oh, 5 minutes. Okay, thank you. It just got downgraded. It's okay. There's a tension parameter here, and we'll see in action what that actually means. So I'm not going to spend too much time on that. Okay, so here's our first closed Catmull-Rom splines rendered for different tension parameters. The very nice thing about the Catmull-Rom spline is if your tension is 1, it actually gives you a piecewise linear solution. So this is an actual sharp edge here. This is an actual honest-to-good piecewise linear polygon here. And for high tension, it starts overbending, but there's so much tension in there, and you can make that pretty extreme. And for decreasing tension, it gets more and more lax, and in fact, it starts underbending at some point. So this is it's kind of a symmetric shape, sort of a variation on a circle. And here's a more gnarly shape, just to play with this setup, right? I'm going to skip this, because in a paper, you have to show spectra. In an audience, you play the sound. So like you can hear this. And this we'll also hear, but I just wanted to quickly explain these figures because they're interesting. When you deal with nonlinear oscillators, right, with chaotic oscillators, they have very complicated parameter behavior. And so how can we see what's going on, right, without having to study the equations in minute detail? And one way of doing it is these parameter planes. And this is out of the dynamic system literature, but I've sort of played an auditory variation on this. This is feedback FM here. And the colors is derived from a spectral notion where you compute FFT, you sort the bins by energy in it, and then you find how many pins do I need to get to the mean. If there's just one peak, just one bin will give you all the energy. And if it's a very flat spectrum, you're going to need to integrate over the whole thing. So it's a good measure to give you a sense of peakiness. How few peaks do you need to capture the energy? So blue means one peak, and red means very flat spectrum. So that's a way we can sort of read these diagrams. And these tongues here are called Arnold tongues. They do mode locking. There is fixed point areas. There's all sorts of fun stuff in there. And here we have a circle, a deformation as a diamond and as an L shape, and you just see there is more base energy in these deformed shapes than in our circle, even for a chaotic oscillator like the feedback FM. But we can go crazier. We can actually not only deform our modulator, we can also deform our carrier. We can deform both at the same time, and this shows what happens when you do both, right? We take a circle as our base, as a carrier, diamond and L-shaped, and you get all sorts of funny distortions in your parameter plane, and you can see for the LD, you start being asymmetric and so forth. And I have 2 minutes, so you know what? Screw all these equations. You guys want to hear some noise, right? That's what we hear. Okay, so let's do this, and I hope it's just going to be nice to me. You guys hear anything? You may have to crank that just a little bit. I don't get any sound? Okay. Oh, yeah. Sorry. Okay, free torture courtesy of me. Sorry. Okay, so we have our tension parameter here. And I might be able to do a sensible approximation of a sine shape here. And we can just play with the frequency. So this is boring. We know all of this. Right? See if I want to do frequency modulation in the standard form. I can try to play the same game. I can try to make this a circle. And I turn on my modulation. Sounds like FM. Okay, we're doing some FM here. But of course, I promise that I can deform this. So now we're doing FM, where our modulation shape is this weird thing. And by the way, I'm just doing these performance gestures, but actually it turns out this one isn't doing anything, right? Because actually the Cadmium-Rom parameterization is per axis, so they're independent, but it's still satisfying to use that performance space. And I can, of course, do that with both of these. More subtle over here, and I can give you all sorts of shapes. Anyway, so this is now FM generalized to these shapes, and we can just FMize with clover leaves or whatever you want to do. Finally, torture warning, let's do chaos. Okay, so I'm going to do feedback FM, and I hit a fixed point. Perfect. Okay, so this is our quiet phase. And I'm going to, okay, well, this is a little too much quiet, so let me crank up the chaos. Right? So this is a chaotic oscillator in a highly chaotic regime, but because of the topological construction, I have complete faith it's stable. Like nothing is going to blow up on me, this is always going to work, and it's going to work on any shape. So I'm fine, I can just keep going, right? This is how, and if it's pleasant or not, that's the job of the composer to find out. It's not my job. And I'm out of time, so like, I'll just stop the noise here. Is there a question over there?
I think you may have DC components to deal with while changing.
Yes, so I'm not trying to remove any DC here, and you can get DC components. I'm not sure why I need to remove them. Do you hear anything that you would consider DC? But we can't hear DC, so that's why I don't care to remove them, because yeah, they're in there. You can get DC offsets in these oscillators and so forth, but they're not auditorily relevant, so I don't take them out. I've actually been lazy here. You may have heard some crackling, because I don't interpolate parameters at all. I just do raw changes per buffer size. You can make this all cleaner than what I did. This is.
I think when the volume went down, as you moved the, say, the center of gravity of the left circle, that was because a DC probably is going into the system and then disappears.
Yeah, so you can definitely, if a DC kicks in, that step you can hear, right? And I'm not smoothing anything. You could take care of that with like smooth interpolation of your parameter changes and stuff like that, like our standard techniques to make this better behaved. Yes?
Maybe I got you wrong, but you have these high-dimensional topologies which you run up, and then you project them down to a number line to generate the sound.
Yeah.
Did you try modulating the projection?
So in this example, and I didn't say this, this is projecting down.
It's just the x-axis, yeah.
And I chose an orthogonal projection. The only reason why I chose the orthogonal projection is because I want to tap into your sort of visual intuition, the way your brain likely functions. You can pick any projection you want. You can pick some crazy projection function that you want. That all works. It's guaranteed to be stable, right? Yeah. So it's another playground to play with that you could deal with. Yeah, absolutely. Okay, all the way back there.
Can you turn up the number of points that you have?
So not in my demonstration. In fact, technically, the underlying engine could. I decided not to because it actually ends up for this closed loop here. Yeah, you could do finer radius control over there and so forth. Like in the principle, doesn't change anything. But yes, the algorithm works for more control points. You can keep adding more. And in fact, it doesn't even cost you anything, right? Because you do a modular function to find which segment you're in, and then you do the interpolation in the segment you're in. So you always only interpolate one thing.
Right.
And so this scales nicely with more segments.
Cool. Thanks.
Absolutely.
One last question.
We have one over there. Oh, sorry, I don't know. I think I saw yours first, I'm sorry. Sorry. We can talk after.
I was just curious, when it's in a chaotic regime, do you ever have to worry about the function sort of degenerating to a point or stopping?
So these are nonlinear functions. They can be converged to fixed points, absolutely. The funny thing for me is, like, once you get used to them and you really want to be in the chaotic regime, fixed points are not that dense. You just vary your parameters a little and you will find something interesting. In fact, maybe if I may, just a quick illustration. This is in a chaotic regime. See if we can find a fixed point.
Yeah.
We don't find any fixed points just going around here. You see my point? Mm-hmm. But you saw this in this diagram. This upper area was very dense. But as long as you stay out of the side triangles, it's all filled. It's like most of these are sound. So it's, in practice, it turns out to be a rare thing. So much so that if you interactively control, like, you basically run over it and you don't even know that you jumped over a fixed point, that sort of stuff. But I couldn't find one just now.
Thank you.
So thanks, Georg.
All right.